So you may remember that these questions were a really nice mix of resolving either horizontally and vertically or parallel and perpendicular to the slope, and Suvat. And with these connected particle questions, we tend to deal with them as two separate entities, but they have some things in common. So in this question here, the tension in the string will be the same, and the acceleration that they're experiencing will be the same. So I predict that there's going to be a little bit of equilibrium, because resolving this vertically, R is going to equal 10g. There's going to be a little bit of Newton's second law, F equals ma, because resolving this horizontally, I've got an acceleration in that direction. And there'll be a bit of Suvat as well, because I'm told something about the acceleration, and it may well be that I need to use Suvat to calculate other things. So I think the best way is always just to have a punt and have a start. Remember, F is the force of friction, and that is at its maximum value, mu times r, and we're asked to find mu in part B. So I'm going to start with A, and I'm going to resolve horizontally, vertically, sorry. And I'm going to deal with A and B separately. So have a go, see how far you get with this. The maximum value of friction, which will always be in effect when it's moving, friction will be at its maximum value, is mu times r. That's why I'm starting by resolving that. I'm going to call to the right positive. I can choose whichever direction I want to positive, but it makes sense in this case because that's the way it's accelerated. Friction always resists the movement, so that's why in this case friction is going against that movement. So Bit stuck here. I've got two variables and only one equation. I know what f is, but that's still got mu in it. So, dealing with A has got me so far, but I can't really get any further. So what I'm now going to do is look at B. I'm going to deal with B. Now with B, I'm only going to resolve vertically. There's no horizontal movement at all. But that might help me. Some of you may have chosen to go that way first, which was probably a little bit more sensible.
So,
Yeah.
why is 8G there, but it's only 10 there?
Because it's two different particles. That's A.
Yeah. So that's F equals MA, isn't it? What you just did.
Yes, so A weighs 10 kilograms and B only weighs 8 kilograms.
Yeah, but then you did F equals MA, and you did 8G, and the first one you just did.
Oh, right, no, I did 10G.
Yeah.
So F equals MA, the mass of that is 10,
Oh,
right?
we not doing that.
Mass is 8.
Okay.
So yeah, so the force is 8G, but the mass is 8. So that's F equals MA. I chose to make down positive just because I knew it was moving downwards. So that's all good news. I've got a value for T by resolving, by just looking at B. So T, 74.4 newtons. And then I can come over here. Now I know what T is. I know that F is mu times 10G. So I've got T, which is 74.4 minus mu times 10G equals 5. And then it's just a bit of algebra jiggery-pokery to work out the value of mu, which should be between 0 and 1. 74.4. Did I say we'd finish off the example? You can always look at the video these days, don't have to check. I have a feeling we left an example half complete, but anyway, we're into this now. So, yes, 69.4. They have 2 decimal places in there. Any questions about that one? So we're going to have a look at number 3 now. Oh, I didn't mean to do that. They throw a little bit of a thing in the works with number 3 because there's friction up here. This is a rough plane, so there's a force of friction resisting the truck as it moves that way. But it says for some reason this is a smooth plane, so there's no force of friction resisting this. So the only force pulling down here is 800 G times the cos of that angle there, which is 65 degrees. But again, this is a problem where I'm going to deal with the 2 parts of it separately. We've got the added complication of the angle, but we're used to dealing with angles now. So I'm going to deal with the car, and I'm going to deal with the truck separately, but they have T and A in common. So the T here will be the same as the T here, and the acceleration pulling it up the slope is the same as the acceleration pulling it up the slope. And this time, there's a little bit of Suvat involved, because they tell us it starts from rest and it goes 10 meters in the first 30 seconds. So I can work out acceleration from that little bit of information using Suvat. So my first thing I'm going to do is to use Suvat to work out the acceleration, which will be the same for both. And then I'm going to look at the car, and I'm going to look at the truck separately. Start with Suvat. Now the Suvat formula are on the formula sheet on page 8. You can't remember them? A couple of formula books there. Oh, I'll read. No friction for the car because it is on a smooth slope. slope, we resolve parallel and perpendicular to the slope. Please work at your own pace, and if you are stuck on a later question, please ask. Don't feel you have to. I mean, they're quite nice works.
You know tomorrow?
Yes.
Is there going to be, I can't remember, is it like parametric functions? You know, when you have to use like sine and cos and like use a trig equation?
Well, certainly changing parametrics into Cartesian is on there.
Yeah.
And I can't remember whether it's a trig one or a non-trig one. I genuinely can't remember, so, but it could potentially be that, yeah. But you'll have a formula book, so you'll have access to all the identities, even though some that we have to derive. Yeah, while I think of it, tomorrow period 2, I can't endorse you bunking off other lessons, but if you're available, the other group has their lesson during that time, and you're very welcome. We're just going to do a revision. I'm not going to teach anything, they're just going to work through revision, and I'll be around to help. And then we're in here for the exam, period 3. The only force pulling the car backwards is its weight at an angle of 65 degrees, so that's why the force pulling it down is that, and that equals mass times acceleration, which hopefully you've already worked out by using Suvat. So don't always use Suvat. I'm not sure there's any value in resolving vertically then, or parallel to the slope. Can I strongly suggest you leave A as 1/45 because it's a recurring decimal, I think, isn't it? Well done, yeah. Yeah, that rings a bell. Yeah. Always worth storing those values. I forget if you need it in the next part, but. Yeah, it always seems funny rounding big numbers like that to 3 significant figures, doesn't it? So I'd always write it with a ... and then put underneath equals to 3 significant figures. In most cases with friction, it helps to resolve vertically first, because that tells you what R is, which you need to work out what F is, and you then use F when you resolve horizontally. So we didn't need to do that here because there was no friction. But in this case, we've got friction, so I'm going to start by resolving vertically. I'll start by calibrating as well. So it all comes together quite nicely. So I've worked out T in the first part, which I then need to use here, because that's the same as the force pulling the truck backwards. I also need F, which I've just calculated by resolving vertically. And I need A, which I calculated earlier as well. T and A are the same with these connected particles. So it all ends quite nicely. Just going to go for 2 more minutes, give people a chance to finish that one off, and maybe make a start one of the others.
So,
Yes,
where does the superficial from?
in the question.
Is it?
It says right at the very start, above the diagram.
Okay.
That's well done for asking. Always good to ask. Well done. I'm sort of hoping that, having done these really tricky problems, the sort of ones that we were doing last week, which I've said, equilibrium involving friction, that's all that's going to be on the assessment. It does seem really easy peasy. I'm just going to tell you the answers in case you hadn't found them in the back. And you get W is, big old number, 19,055.54 newtons, which rounds to 19,100. I'm not going to do the last part, but if the rope breaks, then you've no longer got T and the acceleration will change. But you've still got W and you've still got F. F will stay the same. F, if it's moving, F is at its maximum value. Remember, friction is variable until it reaches its maximum value, and then it stays at that value, and its maximum value is mu r, which we've already calculated. So in part C, you would have W, the driving force, still the same, minus friction, still 1600 G, equals mass, still 2000, times acceleration. So actually that's quite an easy question to answer in part C. These are really tricky, and I know your mind is on other things at the moment, and it's not even on the assessment after half term, but it's worth, if you want to challenge yourself, having a go at some of those. We will, on one of the remaining lessons, we will do a bit more practice of this. We'll do a sort of bit of general practice. Can I just move on though to a different sort of connected particle problem? I'm sorry for some of you that leaves you in the middle of a question. So far, we've only done problems where we've dealt with the different elements in the question separately. But you may remember with connected particles last year, so things like cars towing trailers, we occasionally dealt with them as one unit, so we sort of threw a blanket over it and we dealt with it as one thing that was accelerating with a mass that was the combined mass. And you do get connected particle questions on slopes of that type. So for example, you've got a couple of blocks here connected, and sometimes in questions like this you need to consider the separate elements like we've been doing for the two earlier questions, and sometimes you throw a blanket over and deal with it as a single particle or a single weight. And I have to say, the next two questions that we're going to go through, I worked through, and I found it really tricky at first to decide which was which. Do I deal with them as separate blocks on a slope, or do I deal with it as one big block? It doesn't matter, because if you do it the wrong way, you'll just get stuck and you'll go back and do it again. So it's not a huge problem. So let's have a look at this problem here. We've got two objects, and they're connected by a rigid rod, and they're being pushed up. So they're moving, so there is friction. They're going up, so friction's going to be going backwards. There'll be friction here, and there'll be friction here. Interestingly, they're both the same mass. So friction will be the same, because friction is mu times r, and r will be the same because everything's... So in this question, we're asked to calculate the thrust force in the rod. So the difference between a rod and a rope is that if it was a rope and I pushed there, the rope would just sort of fold and collapse and it wouldn't have any effect. With a rod there, me pushing here, well, from the point of view of this block, I'm being pushed here by the 20 newtons. I'm going to feel the rod poking me here, aren't I? So there's a force coming down into that. And if you're that block, you're going to be shoved up. So that's the difference between a sort of thrust and a tension. So my question is, looking at this example, and in particular what they want us to work out, are we better to consider this as one complete unit or as two separate units like we have been doing? Would anyone like to have a punt? It's a 50% chance, I reckon, isn't it? But
Complete unit.
you're going for complete unit, Pat? Would anyone like to agree or disagree with Pat?
I'll disagree just for fun.
Well, there you go, yeah. Well done, Isabel, you're right. No, but well done for having a punt. No, the reason I think the separate approach works here is because we're asked to find the thrust in the rod. Now, if we deal with it as one big unit, we're not aware there's a rod beneath it. If we throw a blanket over it, we don't actually know what's going on inside it. So it might be that we need to do that first, but in this case, we deal with it as two separate units. But well done for having a go. There's an extra confusion here, isn't there? There's not much that we know. So we don't know mu, so we're going to have a mu in there that we don't know. We don't know m, we're just going to call it m. We don't know the angle, so we're going to call it theta. And the extra confusion there is that means that I know that this angle here will be theta, but this angle here is 90 minus theta, so we have to use sine theta there. You know, I prefer to use cos, but there we go. But it is going to end happily, all right? So can I encourage you to have a look at this problem? No Suvat required. Just have a look at this problem from the point of view of A and resolve parallel and perpendicular to the slope. And then look at this thing from the point of view of B and resolve parallel and perpendicular to the slope. You'll then get two equations that you can combine.
Where's the friction going to be going?
Right, really good question. So for A, I'm going to just draw a picture for A. A is being pushed up the slope by that 20 Newton weight. Doesn't tell us anything about that movement, it's just that it's moving, so that means friction is going to be resisting that. And the fact it's moving means it's going to be at its maximum value, which will be mu times that. And I don't know mu. So yes, there's going to be a lot of missing values here, but I promise you it does end happily. Remember, when you're resolving parallel to the slope, there are three forces: the 20 newtons going up, friction coming down, but also the component of the weight. And because I don't know that angle but know this one, I'm going to call that mg sine theta. Now we're doing more. The other thing I should have said is actually we don't need to do all of this. You may spot which is the bit we don't actually need. So I've got an expression for f with two variables in it, mu and m. G I know is 9.8. Oh, three variables, I don't know theta, do I? So that's not very satisfactory. If I resolve parallel to the slope, then I've got the 20, this is F equals MA, 20 going up, F coming down, and the component of this force. Now, because I don't know that angle, I have to use sine of the angle that I do know, and that equals MA. Don't know M, don't know A, don't know F, although I've got an expression for F. See if you can do the same expression for B. Very similar, but subtly different. Oh, hang on, I've missed, sorry. I've missed T, haven't I? Yeah, of course. And I know they tell you which way T is going. I would have to just imagine that's me. Where would I be feeling it shoving me that way or that way? Or would it be pulling me that way? That's how I work it out. I don't know if you can see where I'm going to go with this. I mean, there's a number of ways of doing it, but we're trying to find T, remember. I've got two expressions which are equal to MA. So I can say that that must be the same as that, because they've got the same mass. So that's what I'm going to write. And you'll know I haven't substituted F with mu mg cos theta. You'll see why in a minute. So looking at my two equations at the bottom there, they're both equal to MA, so I know that, which is the left-hand one, is the same as this. And as I said, I've got an expression for F, but I'm choosing not to put it in, because I hope you can see what I'm going to do now. I promised you it was all going to end happily. Look what now happens. If I add mg sine theta to both sides, and add f to both sides, and add t to both sides, I get my answer. You could have done it by rearranging both equations to say t equals, which would have given you f, but that wouldn't have been helpful. You could have rearranged them both to say f equals, but they seem to be the easiest way. So actually, this was unnecessary. It wasn't necessary. But we didn't know that when we started, because so you know it doesn't matter. So that's an example of a problem where it was better to deal with these two things next to each other as separate entities. So I'm not going to embarrass you by asking the same question of the next one, because you can probably guess the answer. Here's a similar problem where it helps to deal with them as one single entity. So there's an awful lot going on here. We certainly know a lot more about this problem. This is page 136. If you But the reason I think this works, well, the reason I know that it works better to deal with it as one single unit is I tried it as two separate things first and got myself in a right mess. So it's better to deal with it as one single unit. And when I do that, remember we're throwing a blanket over it. So we've got no idea what's going on underneath the blanket. All I know is that I've got something which weighs a total of 5 kilograms. So I've got something with a weight of 5 kilograms, sorry, a mass of 5 kilograms, so its weight is 5g. I know that it's got a reaction force, R, which is the sum of both reaction forces. But because I've got my blanket thrown over it, I can't see that that's two things, that's just one reaction force. And because it's moving up the slope, I know the friction force is going backwards, and that's one combined friction force, which is the sum of the two separate friction forces. The fact I am dealing with it as a single unit means I'm not aware of the tension in the string between the two. I do know that it's being pulled up, though, by a force of 48 newtons. The angle is alpha, and interestingly, I'm not sure we've come across this before, we're told tan alpha. Now we've done questions where you've given sine alpha, and you can work out cos, and then when you know cos you can work out tan because you know sine and cos. If people say, well, can't I just do shift tan and then cos it and sine it? Well, you could do. The proper way of doing it is to use the identities, and there is an identity linking tan squared and sec squared. However, we know it's acute. We know this angle here is acute. So what we can do is say, okay, if it's 3/4, that could come from a triangle like that. And if that's true, then Pythagoras tells me that that's 5. So I can work out sine alpha and cos alpha. Sine is opposite over hypotenuse, and cos is adjacent over hypotenuse. So go on, see if you can go through the process here. The magnitude of the acceleration, we should be able to work out by just dealing with it as a single entity. Remember, to work out friction, we need to start off by resolving perpendicular to the slope to work out R, and then mu times R will give us F, and then once we know F, we can resolve parallel to the slope. Have a go, have a go. The question goes on, which we probably won't get to, some of you will, I know. Thank you for that. You haven't seen that beam like that, but he was Yes, it may be on its way to him, but yeah, it's great. Don't forget the weight has a component here. I don't know the angle, so I'm going to have to use sine, but I know what sine is. So force is going up the slope, 48. Force is coming down the slope, the friction resisting that movement, and I've worked out the size of it because I resolved perpendicular and multiplied it by mu. I've also got the weight, don't know that angle, so I have to use sine of that angle, and I know what the sine is. And that all works out nicely, and it's so you may think it's pointless resolving perpendicular to the slope because it's not moving in that direction, but that's essential to work out friction. So friction is this weird force that links the horizontal and the vertical, or in this case the perpendicular and the parallel. Okay, so something cropped up in a question with the other group the other day when they were revising differentiation. And I showed them how to do something, and I don't want you to miss out. This isn't on the assessment, but what cropped up was differentiating. Now we have already done this by writing the right-hand side as e to the ln of x, which was horrible. There's a much easier way of doing it now. We've done implicit differentiation. So I just very quickly want to show you, so I want to make sure I'm the same for everyone. So if you were asked to differentiate this, and it crops up in several questions on those revision papers, log both sides to start with. I haven't differentiated yet. I'm just logging both sides. So I get ln y and ln of 2 to the x. Haven't differentiated yet. I can then use my third log rule to rewrite that as that. Remember, log 2, ln 2, is a constant, so that's a bit like 3x or 4x. Now I'm going to differentiate. I'm going to differentiate this as an implicit function. So when you differentiate things implicitly with respect to x terms you just differentiate as normal. So if that was a 2x, it would become 2. If it was a 5x, it would become 5. It's ln 2 times x, so it just becomes ln 2. Y terms, you differentiate them as normal, but then multiply them by dy by dx. So ln of y, when you differentiate ln of x, you get 1 over x. So ln of y, you get 1 over y, multiplied by dy by dx. I'm then going to multiply both sides by y. So I've got dy by dx, but it's in terms of y, which is a pain. But if I look right back to the beginning of the question, y is equal to 2 to the x. And hopefully you can see that would be the same for 3 to the x, 4 to the x, 5 to the x, 6 to the x. And you can use that as a standard result. It's not on the formula sheet, but you know, you can if you're asked to differentiate 2 to the x, you can say that's 2 to the x, ln 2. So I just thought I'd better show you that. Like I said, it doesn't feature in the assessment, but I want to try and make sure I'm dealing with everyone evenly.